This is Dr. Holt. This video is on AP Physics C, an introduction to rotational kinematics. Rolling motion is very similar to what we've done in linear motion. Instead of dealing with distance, we'll be dealing with the angle, where the angle is going to be in radians. If we look at this plate here, the circular plate, then we can say S being, let me put this in red, the distance S along this arc length here is going to be nothing more than the radius of the arc, the radius of this plate times the angle, and the angle will be in radians. If I multiply those or take the product of that, I will get the arc length from here to here. We can also say that the delta between here and here is going to be the radius times the change in the angle here. Now, angular velocity, which is defined as omega, will be defined as the rate of change in the angle or angular position. Angular velocity is also related to the frequency of rotation. Angular acceleration, using the Greek symbol alpha, will be defined as the rate of change in angular velocity. So you often see omega being measured in radians per second, or change in the angle over change in time. We can also say that omega is equal to 2 pi times frequency, where frequency is going to be defined as the cycles per second. Now, the alpha, being the angular acceleration, is going to be the change in the angular velocity over change in time. And again, this units of this will be in radians per second squared. Uniform rotation most often occurs in objects being rotated by motors, such as this device here, or being manually spun into a circle. If we compare the kinematic equations that we're used to, here I've listed this one, and this one. All we've really done is we replace the S with the angle in radians. We replace the velocity into angular velocity, omega. We replace the acceleration into angular acceleration using alpha. So the equations are very similar. A point on a rotating object is actually being accelerated in two directions. So I can have angular acceleration as it goes around. When I have angular acceleration, if I take the angular acceleration and I multiply it by the radius, I will just get the tangential acceleration at that instant in time. Now, the other acceleration you're always going to have is radial acceleration, or the centripetal acceleration back in. So if the actual acceleration is going to be nothing more than the addition of the two vectors, the centripetal acceleration or radial acceleration and the tangential acceleration, that's always going to give me the magnitude of the actual acceleration at that point in time. Okay, I want to work a few problems. I think by working some problems it'll clarify the rotational kinematics. First problem, I have a wheel rotating with a constant angular acceleration. It's going to turn through 16 revolutions during a 2-second time interval. Its angular velocity at the end of this time interval is 12 radians per second. What is the angular acceleration of the wheel? Note that the initial angular velocity is not 0. Alright, so we're going to kind of demonstrate what's going on in this picture here. I know this value here, which is omega naught. Initial, we don't know what that is. At some point in time, it's going to go around 16 revolutions. Its angular velocity at the end of this time interval is going to be 12. So out here, I'll make this out here. We know omega at 2 is going to equal to 12 radians per second. We also know there's acceleration taking place. And that acceleration is going to be alpha, and we don't know what that is. The other thing we know is we have time. And time is going to equal to 2. Now what we need to do first, we need to find out how many radians has it traveled in those 2 seconds. Now we would know that it's traveled 16 revolutions. So we've got to convert that to radians. Now there's 2 pi radians in 1 revolution. So just multiply that by 2 pi radians, which is the same thing as 1 revolution. My revolutions will cancel out, and I'll be left with 32 pi radians. Okay, so that's going to be my angular displacement in the 2 seconds. Alright, so let's go ahead and write down our equations and we'll be able to solve this. Our final at 2, we can say our angular final position is equal to our initial position, naught, plus our angular velocity times t, plus 1/2 times our angular velocity times t squared. That's going to be our first equation. Our second equation that we may have to use, we have our angular velocity final is equal to our angular velocity initial plus our angular acceleration times t. And our last one is final angular velocity is equal to initial velocity squared, these are both squared, plus 2 times our angular acceleration times the change in our angular position. Alright, so now let's look and see what we know and what we don't know. Okay, we know, only thing we know is we don't really know final position, do we? Let's see, wheel rotating at constant angular acceleration through 16 revolutions during a 2-second time interval. Well, actually we do, we know. We can let this value here go to 0. And we do know this. Now this value here, I should have noted that. That's going to be our initial. We do not know this value here. We do not know this value here. But we do know time. If I come to this equation here, I know my final. My final is 12 radians per second. I do not know this. And that's noted that the initial angular velocity is not 0, so we don't know that. We don't know this, but we know time. We come here, we know this. We do not know this. I should have made that not, it's the initial. Same thing. Should be consistent though. We do not know this, but we do know this. Alright, interesting problem because we have 2 unknowns. So we're going to have to do some substitution here. Let's see what we can do. Let's take this equation right here and let's solve for, let's see what we want to solve for. Let's solve for our initial. If we take this equation here, can I not say that the initial is going to equal to the final minus alpha t? Okay, we do know that. Alright, let's take that and put back into this equation here, and I think we can solve the problem. So rewrite this. We know our final position, which we noted was 32 pi. So we'll take 32 pi plus the initial angular velocity, and our final is going to be 12 minus angular acceleration times time. Now we're going to multiply that times t plus 1/2 times angular acceleration times t squared. But we do know what a t value is, so we'll take t value, and we know t is going to be 2 in this case, here, and here, and here. So I'll put that in red so you can see that. That would be 2, that would be 2, and that would be 2 squared. Alright, so run these numbers. And again, let me go back here. I should have put an equal sign in there. I apologize. That gives me 32 pi. We're going to distribute the 2. That's going to give me 24 minus 4 times angular acceleration. Plus, in this case, that's 4 plus 2 times angular acceleration, like that. We will go ahead and subtract. That gives me 32 pi minus 24 is equal to negative 2 times angular acceleration. We will divide by negative 2, both sides by negative 2. Negative 2 will cancel out. We'll go ahead and get those values right there. When we do that, that gives us an angular acceleration is equal to negative 38.27 radians per second squared. And that would be the answer for the angular acceleration. Okay, that problem's a little bit more challenging in that you have two unknowns. Alright, let's go to the next problem. At this one, at time equals 0, a wheel is rotating about a fixed axis at a constant acceleration, or constant angular deceleration. So immediately we know that alpha is equal to negative 0.27 radians per second squared. Has an angular velocity of 3.8 radians, and that's okay. This is time equals 0. We know omega, or angular velocity, is going to equal to 3.8 radians per second, and we know that theta is going to equal to 8.5 radians. What is the angular position of the wheel after 2 seconds? Alright, then we can go back again to the rotational kinematic equation. We can say the position at 2 is going to equal to the initial position plus the angular velocity times 2. I'll put these numbers in, plus 1/2 times angular acceleration. Again, I'll put these values in at 2 squared. Now let's put these values in and we can solve this problem. Our position at 2 is equal to our initial position, which is 8.5, plus our angular velocity, which is going to be 3.8 times 2 plus 1/2, and make sure you make that negative 0.27 times 2 squared. We'll put those values in and see what we get very quickly. Okay, so I get 8.5 plus 3.8 times 2, okay, plus 0.5 times negative 0.27 times 2 squared, and that gives me 15.56. So my position at 2 would equal to 15.56, and again those units will be in radians. Okay, the next problem, I have a bug. It's on the rim of a 78 revolutions per minute, 12-inch diameter record. The record moves from rest. So we know then, oops, I'll do this in black. And we know omega initial is equal to 0. Final angular speed is going to be in 3.35 seconds. Find the bug centripetal acceleration, 1.5 seconds. Alright, we'll take this value here, which is 78 revolutions per minute. We'll convert that to radians per second. Oops, don't want to do it with the racist. I don't want to do equal, I want to multiply. So we're going to multiply that by 2 pi radians over 1 revolution. Revolutions will cancel out. We're left with radians per minute. We want to go to radians per second. I put 1 minute up here. I put 60 seconds down here. Minutes will cancel out here and here. So run that through the calculator very quickly. So we got 78 times 2 divided by 60. So I'll leave it in pi just for right now. That's going to give me a value of 2.6 pi radians per second. That will be my angular velocity after 3.35 seconds. Okay, we want to find the centripetal acceleration at 1.5. So we need to find, probably first is to find out what the angular acceleration is going to be, because we don't know that. So we can go back to the equation that the final angular velocity is equal to the initial angular velocity plus acceleration times t. We know this value here is going to be 2.6 pi. We know it's going to be initial is going to be 0 plus our angular acceleration, and then our time it took to do that was 3.35. So we'll solve for that, and I'll go ahead and I'm going to get rid of the pi. So 2.6 times second pi. We will divide by 3.35. That gives us an angular acceleration of 2.438, and again that would be in radians per second squared. So now we have this value here. What we need to do now is to find out, and I'm going to kind of draw a picture of what's taking place here. Let's draw just an arc, a circle. And let's see where the bug is located. The bug is on the rim. So what I have is I have a bug sitting out here. I'll do this. The bug sitting out in blue. We need to find out what the bug's tangential velocity is going to be. If we know what the tangential velocity is, then we can find out what the acceleration is going to be back into the center. Now what's taking place, I'll pick a spot approximately where the center is going to be, is we need to find out what that velocity, angular velocity, is going to be at the 1.5 seconds. Now we can do that very quickly using this equation here, because we know the angular velocity at 1.5 seconds is going to equal to the initial, which we said was 0, plus our angular acceleration, which is going to be 2.438. We're going to multiply that by our time, which is 1.5. We do that, we will find out that our angular velocity at 1.5 is going to equal to 3.657 radians per second. We also know that tangential velocity is always going to equal to our angular velocity times our radius. So I need to find out what this velocity is here. This is my tangential velocity. So my tangential velocity would equal to 3.657 radians per second times my radius, and the radius is 12 inches. So multiply that times 12, and what we will get would be 43.89, and that would be in inches per second. That's how tangential. We'll find out what the centripetal acceleration will be in terms of inches per second squared. We know, let's just see real quick too, all we're looking for is centripetal acceleration. We know centripetal acceleration is going to be nothing more than velocity squared divided by the radius. So we take our value here, 43.89 inches per second. We will square that, and we will divide that by 12 inches. That'll get us our units in inches per second squared. So we square that, and divide by 12. That gives us a centripetal acceleration of 160.5 inches per second squared. Okay, so that problem's not too bad. So far the hardest problem has been that first one I worked. I'm going to work one more, In this problem here, I have a mass here attached to a 50 centimeter, so we'll make that just 0.5 meters. Starts from rest, so it's going to start from rest. Then we know our angular velocity initial is going to equal to 0, and it's going to rotate 40 revolutions in 1 minute before reaching an angular speed. Okay, before reaching final angular speed, determine the angular acceleration of the mass. Okay, so we can find out what our final is going to be because we know it rotates 40 revolutions in 1 minute. So we know our final position is going to equal to 40 revolutions. We will multiply that times 2 pi radians per 1 revolution. When we do that, that'll give us 80 pi radians. Okay, now let's go ahead and we know our time, also 1 minute. Time is going to equal to 60 seconds. Let's go back to our kinematic equations. I should say our rotational kinematic equations. We know our final position is going to equal to our initial position plus our initial angular velocity times time plus 1/2 times our angular acceleration times time squared. Alright, we want to find angular speed and we need to find angular acceleration. Alright, let's see if we can do this. So let's say we did 40 revolutions in 1 minute, so we know this value here is going to be 80 pi. We know it started at 0 here, so we can put 0 into here, plus 1/2 times our angular acceleration times 60 squared. We will solve for angular acceleration, and our angular acceleration will be 0.1396 radians per second squared. Okay, now we want to find angular speed. We just go back and use the equation that the final angular velocity is equal to the initial angular velocity plus our acceleration times time. So final equal to, this value was 0. Put in our angular acceleration. We multiply that by 60 and we will get our value of 8.38 radians per second. Okay, there's our two solutions. Okay, and I hope that helps you. Here I've worked 4 problems. I've kind of gone through the definition of the kinematic equations using rotation. Again, they're very similar to what we did when we did our basic kinematic equations, when we did a more linear type motions. So anyway, I hope that helps you. I wish you the best of luck on these type of problems.